Okay. So in the last few classes, we had been talking about, like we had been discussing issues like missing values, anomalies, extreme values, and things like that. Today we will consider a different topic, which is still related to this spatiotemporal data mining, but it like here like we will consider a different sort of tool. This is aimed at understanding the like physical connections or the spatial connections between different locations, as well as like maybe potentially dividing the entire region into smaller groups where like which seem to be working like as in a more homogeneous way. Okay. So one way to do this is by with the mathematical constructs of networks. So network is something which, or network or graph, it's something which most of you will be familiar with. So like it's basically a collection of nodes and edges. So there are a certain like a set of nodes and some pairs of them may be connected by an edge. So each node basically represents some kind of an entity, and the edges basically represent the interactions between the two entities. Like so, like for example, like we know there can be computer networks, social networks. So like for example, in case if we are considering as a social network, like the different nodes will be the different persons, and the two persons or will be considered to be connected by an edge if they know each other, or if they interact with each other, or if they are connected with each other on a particular social media like Facebook. In case of like protein networks, like the different proteins will be the different uh, nodes, and then like two proteins will have a node among them depending on the nature of interactions between them. And these kinds of edges can be either undirected or directed. Undirected like so if two so it depends on whether the interaction is one way or two way. So if two people are acquainted with each other, it's a two-way thing. But proteins may like when two proteins act interact, or when some or maybe some when some other factors like impact different proteins, it's not really a it's not a like it's not a mutual. The nature of the interaction is not mutual. It's like uh, one is acting on the other. So in that case, this kind of asymmetry is best represented with the help of arrows, or directed edges. Similarly, like we can have road networks or railway networks, in which the different nodes might be the railway junctions or the road junctions and so on. And in case the edges in that case is like two junctions will be considered to be connected by an edge if they or and by an undirected edge if traffic can flow both ways. But if traffic can flow only one way, as it often happens in on various roads which are marked as one way, then they have to be indicated uh, as a directed arrow. With the direction of the edge basically indicates the direction in which the transportation might take place. So what is the use of considering such networks? One is to study the nature of the interactions. It's the most important, the fundamental reason why people study networks is to understand the interactions between different entities which are represented by the nodes. So these need not be only two the interactions between any two entities, but it can be the interactions between multiple entities. In fact, it is that which is more important. So basically what people do, one of the most common things which people do when given a network is to identify communities between them. So what are communities? Communities, as you understand in a social network, a community is like a set of individuals such that within that set there is a density, there is a high density of edges, means within that like almost everyone knows everyone else. But Beyond that set, there are like relatively less edges. That is so like we will say that these few people for like maybe these few people form a community if like any two of them are linked together by an edge with high like this. But if you consider edges between any of these people and people of who are outside this set, then we will see very less frequent number of edges. Okay, so that is like what is meant by communities in a network. So for example, common interest groups in social networks, or like when we have that like whenever we are dealing with some kind of chemical agents or say proteins, etc. Also we see these kinds of interactions. That is those those elements or those proteins which interact with each other, they can be considered to form a closed community. But then there are also pairs of chemical elements or chemical compounds which do not interact or do not react with each other. So we can say that they are not part of the same community. Okay. And another important thing which we like study with the help of such networks is is dynamical processes. Whenever there is some kind of flow of information, say, or something, some quantity from one entity or from one node to another through multiple edges. So that and the these and it might also become the nature of the network itself may be dynamic, where more edges can be formed over time, and some edges may disappear also over time. So the social network, for example, is not something fixed. It's evolves. It evolves. Hello. Yeah, like a social network is not something, it is not a static thing, it evolves over time. So two people may not know each other today, but they may become good friends like 1 year later. And similarly, two friends may not, or two people may be friends today, but maybe after 2 years, they may not be no longer be in touch with each other. So it's a time varying process. And now so these kinds of dynamical things which vary over time, these things are like it's the networks are a very appealing and intuitive way of understanding these kinds of things, these kinds of dynamical processes. So now comes the question of geophysical networks. So geophysical networks basically they can be used to visualize and analyze various spatiotemporal geophysical data, and especially as I said, to identify regions where the geophysical conditions are strongly related. Which and say for example, like identify homogeneous regions in a land where like we see something like common weather characteristics most of the time. So in one of the examples which we had studied or which we had discussed in some of our early classes, we had encountered this kind of situation, like where there is maybe a landmass and there is a mountain range separating the two. And so it may happen that the winds are blowing in from one direction, but those winds are unable to cross the mountains. So it's like on one side of the mountains there will be one kind of weather because it is entirely exposed to the winds, or but on the other side of the mountain those winds do not reach, so it's the weather can be different. Okay. So now suppose I do not know about the presence of the mountain early, but I only have the measurements of different weather variables at different places. So based on that, I may want to identify that this is one region of one kind and this is another like another sub-region of a different kind of weather. So such things, one way to do these kinds of things is with the help of networks. And another is to identify teleconnections. So in in the domain of geophysics, it often happens that like there is some phenomena, some geoscientific phenomena happening in one part of the world whose impact is felt far away from it. So something like it, like if we consider El Nino, which is caused by a strong heating of some part of the Pacific Ocean, where the sea surface gets very much heated up. Is like that is often coincides with very less rainfall in India. And it, on the contrary, when in the same region, when the sea surface becomes cool in some years, or it is not, it is insufficiently heated, that results in often results in excessive rainfall over India. So, although these two things are happening in two different parts of the world, but they are connected to each other through a chain of like intermediate steps. That is due to the heating up of the sea surface in the Neo region in the Pacific Ocean, a certain kind of convections take place, due to which some other like some other things happen, some other kinds of wind movement happens, etc. Over the Australian region, over Southeast Asia, and all those things. Like through a complex chain of events, finally we reach a situation where the like which causes a deficiency of rainfall over India. So to understand these kinds of, first of all, to identify these kinds of teleconnections, that is climatic or any other kind of geoscientific phenomena which happen at different or far apart or very distant locations across the world, but are seem to be correlated with each other. The identification of such teleconnections is one thing, and explaining the teleconnections, that is what are the chain of events through which event A influences event B, that is also or understanding that is also something which we may want to do with the help of geophysical networks. Okay, so but then how to construct a network? So what will be the nodes and what will be the edges? So these kinds of nodes might be there are many design choices related to these kinds of networks, and depending on what exactly we want to do, we may want to construct the network in different ways. Right. So, so first of all, first things first. So, what are the nodes? What can be the possible nodes in a geophysical network? So, one like what the convention which is followed most commonly, but is not necessary. One node may represent a special location. So, like we had all several times been discussing that, like the location which we are studying, like we may like use some kind of a grid structure to divide it into locations like this. Right? Say for example, this is one location and this is another location. So and things like that. So each of these grid boxes can be considered to be one node. Okay, and each node has an associated variable. So depending on whichever geophysical phenomena we are studying, if it is rainfall, then like it's like at every each of the node, we basically measure the value of the rainfall at that location. So it's like every location is associated. Sorry, each node is location associated with a location. Let us say S1 in this case, and the corresponding the value stored at the node is basically the value at I mean the rainfall at that location at a given period of time t. So the values keep on changing with time, obviously. As t varies, then these readings also vary. But these each of the nodes, they are static in the sense that each of them continue to represent the same set of locations. Okay. So basically, it's like saying at if you consider any fixed t, once you have fixed t at then like at one time step, we get an instantiation of the network, which means that at every at every node, one there a value is stored. Right. So at t equal to 1, all the nodes will contain some values. Like at t equal to 2, those values will change and so on. So what we are getting at every instant at t equal to 1, we are basically getting one instantiation of the network. At t equal to 2, we'll get a different instantiation of the network and so on. And if you consider, if you focus your attention on one single node, so that is associated with a location. So over time, you will see a time series of values associated with that node. Okay. So you can like when you are given a node, I mean this kind of a network, you can either look at it at spatially, that is at any given time we are looking at the connections. I mean you are basically looking at the different you are basically looking at the different these nodes and the values stored in them, or you can look at it temporally where you are fixing your attention on maybe one or a set of nodes and you are seeing how the values stored in them change over time. Now next is how to define the edges. When do we say that two edges are two nodes are connected with an edge? So, so whatever it is, an edge is some notion of similarity or some notion of interaction. That is, we can say that two nodes will be connected by an edge either if they are similar to each other or if they interact with each other or something like that. So, in this context, what can be possible measures of such similarity or such interactions? So, like one is the very simplistic thing is of course just physical distance. So, two locations which are close to each other, they may be connected by an edge. Also, the edges may contain, like in graph theory, when we are dealing with edges, the edges are sometimes associated with weights, in which case we call them as weighted edges. And so, yeah, like if the edges actually are on the basis of distance between any two locations, then the the weight of the edge will basically be the distance between the corresponding locations. But that kind of a thing network is not of a great interest to us because that is static. I mean, the distance between any two locations is not going to change over time. So it's like the network structure will remain unchanged. Only the values stored in the nodes will keep on varying over time. Which is fine, but it really does not. I mean, it does not justify why we need a network to express it. We could as well have done it with the help of a matrix or something like that. The network becomes really interesting only when there is some kind of dynamics involved in it, where we understand that like basically something is flowing, something is changing, some new edges are being created, some old edges are disappearing and things like that. So one like a different way of defining such defining these edges is what happens in the case of a correlation network. So what we do is, now let us consider any two nodes. Let's call them as I and J. So as mentioned earlier, each of them are associated with two locations, let's say Si and Sj. And also, as I said, so let us say that at location I, we are measuring one particular climatic variable, let's say Vi, or I mean, not climatic, but a geophysical variable Vi. At the location Sj, we are measuring another variable Vj. Now, these two may be same or they may be different also. No issues with that. And for both of them, we have time series. So as I was mentioning earlier, at if you consider any single node, you will get a sequence of observations. So at node I, you will get this kind of a time series. At node J also, you'll get this kind of a time series. So once you have two time series, or whenever you have two sequences of equal length, you can always calculate the Pearson correlation coefficient between the two. Okay. So Pearson correlation coefficient, as we know, it's denoted by rho. Let's say in this case rho ij, and it's a value which lies between -1 and +1. Now -1 indicates that or +1 indicates that they are perfectly correlated. It means that whenever one of them increases, the other also increases accordingly, and when the first one decreases, the second one also accordingly decreases. And in case of -1, it means they are anti-correlated. That is, whenever one increases, the other one decreases accordingly, and vice versa. Right? But usually those are extreme cases. These kinds of correlation coefficients are never achieved in any geophysical system. We usually deal with correlations like, say, in the range 0.4 to say -0.3 or some things like that. It's like usually it's a weak signal. So what we do is we put a threshold on such these correlation values. Now, what that threshold is going to be like may depend on the exact application which we are considering. So one of the very first papers which dealt with this kind of a climate networks, or this kind of a network, was the climate networks, in which climatic variables, probably rainfall or temperature, one of these two things was considered as early as 2004. And what they did is they identified all pairs of grid points where the correlation coefficient is greater than 0.5. Okay, and such grid points, they were connected by an edge. So this was known as a correlation network, okay, where basically the edges are inserted on the basis of correlation coefficient. Similarly, it's possible to define other pairwise measures between time series between the observations at any two different locations. So that way we can define what is called as a mutual information network, right? So whenever we have two locations, or rather whenever we have two random variables, we can define what is the mutual information among them in this way. Right, so like let us say this is the, let's say that two random variables are called I and j, and their values are denoted by this mu and nu. So it's basically this is the joint probability. That is basically, this is the probability of the event p of x, that probability that xi is equal to mu and xj is equal to nu, right? So this probability times log of the same thing divided by their product. So if the two random variables, if these two random variables are independent of each other, then of course we can write this as their product, the product of the marginals, right? But of course, in general, that will not be the case. So, in case that does happen, in case these two variables are indeed like independent of each other, then this part will of course be 1. So then we'll take the log of 1, which will of course be 0. So like basically we will get in the mutual information coming as 0. But of course, usually that will not be the case. So we'll get some value of mutual information. Okay. So based on, so mutual info, basically mutually, that is, if they are independent of each other, then the mutual information is 0. That is, one does not contain any information about the other. But if they are non-zero, I mean, if they are not independent, then this can be non-zero, and so it may turn out that this can, like, it will be of some non-zero value. So that value will basically quantify how much information about one variable you can get from the other. Okay. Now, so basically it's like the excess amount of information which can be generated by falsely assuming that the two are independent. Now this is all like here. So this is somewhat stronger than the correlation network, in the sense that correlation coefficient is suitable only if the relation between the variables are linear. That's why this Pearson's correlation is sometimes also known as the linear correlation coefficient. But in case the relation between the two variables are non-linear, then this Pearson correlation coefficient is not very useful. In that case, this mutual information is a better way. So on the basis of this mutual information also, we can construct a network. Then another more interesting way of defining a network is is using the concept of synchronization or lag. Okay, so now it might so happen that the time series at two different locations are not perfectly synchronized. That is like, again, consider the example which I mentioned between the sea surface temperature over the Pacific and rainfall in India. So it is generally known that when the sea surface temperature in Pacific gets heated up, then there is less rainfall in India. But this is not, and it does not happen instantly. That is, usually there is a lag of a few months. That is, it cannot happen that one day Pacific Ocean got heated up and immediately on that day the rainfall decreased over India. No, it's not like that. It's not it does not happen. Neither can it happen at that time scale. No, that is as a matter of days, nor is the influence instantaneous. If that, it's more like if for several months the hot the sea temperatures persist, then say during April, May, June and so on, then in the monsoon season of India we will observe less rains. It's like more like that. So when we are considering the correlation coefficient or the mutual information, whatever we are considering, we cannot consider instantaneous value. So when we are saying this kind of a thing, the time, of course, has not been written here, but the assumption is that at any given time, both of them are having these values. Okay. This was the assumption. But in general, this mutual information was calculated on the basis of this assumption. But it may, instead of calculating it in this way, we may also calculate it in this way. Right? So in this, so it's like, instead of that is the event we have considered here is at the same time this xi takes the value mu, xj takes the value eta. This is the definition of our event. But let us say that we define the event in this way by considering this kind of a lag. That is, the event definition is at any given time the value of xi is mu, and delta time points later the value of xj is nu. That's it. So often so whenever they are not perfectly synchronized like this, we basically construct this kind of lag networks, where now what this delta is going to be, we usually do not know. In some situations, the experts may be able to give us possible values of such delta if they already have some idea about at what time scale the interactions may take place. In general, it is better not to assume it. So people like, when data scientists are dealing with this kind of data, they consider multiple values of these lag, and then find for what values this interaction, this whatever is being measured, be it correlation or be it mutual information, at what value of lag this is the maximum. And in fact, without maximum, maximum in terms of absolute values. And also these delta may be delta ij, which means that we may also be considering different lags for different pairs of locations. That is also fine. Okay. So that is doing this may also actually help us to identify the best time lags. I mean, or that the lag at which these kinds of things influence each other. That is something which may actually come as rather than that being provided as an input to the for constructing the network, we may actually construct the network at multiple values and for multiple values of lag and then choose the best one among them. So that is also one way to do it. So like these kinds of studies have actually considered like the how these lags may be used to understand the say the monthly fluctuations and of various climatic variables and so on. So again, so these are possible papers on like on which you may want to give your seminar and or on the basis of which you may want to write a scribe note and so on. Okay, so yeah, so now how to identify the best lag that maximize the correlation I mentioned. Now, so either you can do it like separately for every pair of locations. Now that might be an useful idea in some applications, or it may not be a useful idea in some other applications. So if it is not a suitable, not an useful idea, that is you want a common value of delta which uh, like which is not on the basis of any two particular locations but overall. So in that case, how will you identify the delta? So that is like for example, for that purpose we may want to utilize some other kind well-known algorithms for say for things like sequence alignment and so on. So, so like these are basically some examples of lag time. So, like, so we have so this is the Nino region which we talked about. This is the region of the sea surface temperature in the Pacific, which gets heated up. And so basically, so what we are measuring here is that, like, once that thing happens, then after how many the impacts of these spreads to which other like which other locations after how many days from that and so on. So what is the best lag to consider? So I mean, so I'm not going into the details of exactly what it means, so but what the kind of information which this map is trying to quantify is basically it's basically drawing some kind, it's like in a sense it's like clustering the world map into different regions. Like it's like saying that initially these locations are affected, after that these range of locations are affected, after that maybe these locations, after that these are so and so on. So this is one interesting way of visualizing a lag map. Yet another very useful and important criteria for identifying these kinds of network edges is through what is known as event synchronization. So we can define events for every time series. Okay, so events may be defined as, say, for example, if we are measuring a particular variable, we may define an event as those as a time point when the observation exceeds a particular threshold. Okay, so so suppose we have two time series like this. Suppose we have two variables. One is xi, that is it's measured at location si, and another one xj, which is measured at location sj. So let us say, let's consider the time series at these two things. So this is the time series at one location, and the other it is like this. It's like this. So if you see these two things, if you these two time series in general, there is not the nature of the two time series is quite different, right? So like as you can see, this is the amplitude of this one is quite high. This one, like in this here, it mostly stays around a constant value with very less fluctuations, except for certain time points where there are abrupt rises and so on. But what you may also observe is that the peaks of these two are usually happen close to each other. That is at those. So let us say, suppose we draw like some kind of a threshold like this, and we define, like in this case also we define a threshold like this. So basically we consider those days in which the observations at xi are above the threshold, and the events for xj are those are at like the times when the observations of xj are above the threshold. Okay. So the question which we may be asking is that how often do they have events simultaneously? But now, what is meant by now what event? Event means crossing this threshold. And simultaneously, what do I mean by that? Simultaneously means let's say that suppose on any given time point t, xij crosses the threshold. Okay, let's call the threshold as delta. So synchronize, I will say that the two events are synchronization are synchronized if this happens. So let me call it as delta I. This is delta J. That is, there are two time points t and t prime. The difference between them is is small, is less than a particular quantity, which we have already said. So that is, there are two time points close to each other. I have not said which is ahead, which happens before and which happens after, but let us just say it's like this. Then uh, I will say that these two events are synchronized if this kind of a thing happens. That is that is event at for variable I or variable xi happens at time t, and an event for variable xj happens at time t prime, and t prime are close to each other. If this happens, then I will say that these two events are synchronized. So now I may ask these two questions. I may ask that whenever an event happens with respect to xi, how many times does it co-occur with an event at xj? And similarly, I can also ask, whenever an event happens in xj, how often does it coincide with an event in xi? So if you see xi actually has events, like we can say more frequently. I mean, once it happens, it probably persists for a long duration. Let's say from here to here, let us say it's 3 time points. From here to here, it is 4 time points. From here to here again, it is, let us say it is 4 time points, and so on. So total at 11 time points, we see that an event has happened here. Now the question is, how many of these events have coincided with an event in xj? So here you can see that like one event, one event, one event, these three, and all of them have happened for exactly one day. Okay. So now if you as you keeping delta equal to 0, so here you can say out of the 3 days, on only one day, only one of these 3 days an event also happened at xj. Out of all these 4 days, only on one day an event also happened on in xj, and so on. So basically there are three events. So here we can say that uh, that is from x, that is, if we consider the synchronization of xj with respect to xi, it is actually only 3 by 11. That is 11 events happened, out of which 3 of which coincided with another element, another event in xj. But if you consider xj, only 3 events happened and all of them coincided with an event in xi. So here it is 3 by 3, that is equal to 1 or 100%. Okay. So that means what? That means whenever an event happens in xi, we cannot say that an event will happen in xj also. But when an event happens in xj, then we are more or less certain that an event will happen in xi also. So in that case, we will probably draw like a directed arrow from like xj to xi. Okay, that is, and like I'm not say drawing the arrow from xi to xj, but rather from xj to xi. Why? Because something happening in xi does not give us much information about whether that the same thing is happening in xj or not. But if something happens in xj, then we are more or less confident that something has happened in xi also. So you can say that information, that is, if we have information about xj, then we can also get some information about xi. So there is some kind of, so that's why we use this kind of directed edge in this case. So this is very kind of, and the another important is to note here is the value of the lag delta. So in this case, I have assumed delta equal to 0, but you can also include like delta equal to 2 and so on. If you consider delta equal to 2, then these numbers might change. So here, okay, number of elements is events is still 11, still 11 and 3, but like there are 3 events here, 1 1 1, and like all of these are synchronized with the same event here. That is that these happened at a certain, like at t equal to 1, these two happened at t equal to 2, and these happened at t equal to 3. But the difference between these t equal to 1 and t equal to 2 is 2, which is less than the time window which you have considered delta. So I will say that this event is synchronized with this one. This event is also synchronized with this one, and this one is also synchronized with this one, right? So out of the 3 events happened here, all of them are synchronized with an event in uh, like xj, even though that synchronization is with the same event, but they are all synchronized. The same similar kinds of things can be said about here and this also. So it's possible that in this case, like for delta equal to 0, it was 3 by 11. It's possible for 3 by 11 and 1. It's possible that if you consider delta equal to 2, then it will become something like 9 by 11 and 1. Okay, so if it is 9 by 11, then it's like we can say that not we if something happens, if an event happens in xi, we are like more than 80% sure that it will be something will happen around in xj also, right? So in that case, this arrow can be a bidirectional. That is, information will flow from both xj to xi as well as from xi to xj. So this kind of, so this is another basis of, this is called event synchronization, and this is another very important and interesting way of defining your network structure. And it is very relevant, especially for extreme value analysis. That is, whenever basically, so it's like basically trying to identify whenever an extreme event happens with respect to one variable at one location, then that usually impacts, or that usually is associated with extreme values in which other locations, because extreme values are something to be taken care of. So like if we can form some rules like this, that okay, so the Pacific Ocean this year has got extremely heated up. That means there is going to be tremendously low rainfall in India. So we can take contingency measures like that. So these kind of like if we can, so basically this is helping us to like synchronize these extreme events, so that one kind, if one kind of extreme event is happening, then like it will inform us like which other extreme events may follow it soon, so that we can plan accordingly. Yeah, you can say it's a kind of a warning system for extremes. Okay, so these are various ways in which a network can be constructed, a geophysical network can be constructed. Either it can be on the basis of statistical properties like correlation coefficient or mutual information, or on this or it can be event wise based on these lag, I mean event synchronization, and we also have to consider the effect of lag. Okay, so these are the ways in which these networks are connected. Okay, so now we have got our network in constructed in any of these ways. So now what do we do with the network? How do we analyze the network? So there are various things which various network properties which people study. That is, for example, degree distribution. That is number of edges per node. Every location on an like each location is connected with how many other locations, and that is like are there some regions like with like where the degree density distribution is high, and some other locations where there is low. That's basically hinting at a community structure in the network. So if there is a community, if there is a set of nodes who are mostly connected to each other, their degrees will like be accordingly high. And if there are some other nodes which are connected with very few, like those can be considered to be outlier kind of nodes, which are like basically separated from other parts of the network, so they will have low degree. So this is the degree distribution is one thing. Then degree distribution as a function of a function of distance, that is another thing which people study. So so of course it is well known that and nearby locations will have large correlation, but if you can but can two locations which are far apart, can they also be can they also have high correlation? So to understand that kind of thing, people can study the degree distribution as a function of distance. Okay, then another thing which people do is like they consider the clustering coefficients. That is so basically they try to understand, so these are basically attempts at understanding the community structure of the network. So here we are trying to understand like so you consider any node, you consider any node in the network, and so it will have its own set of neighbors. So so let's say that these this is one node which we have taken, and these are its neighbors. So out of these 5 neighbors, we randomly select any 2 of them. And then we see that are they themselves connected or not. If they are themselves connected, so that means what? That basically means that there seems to be a some kind of a community structure here. That is all like the 2 neighbors of this node are themselves neighbors, right? So that means these things form a closed community. So, so basically, the people try to understand this matter, and like with the help of the local and global clustering coefficients. Again, these are things which I strongly encourage you to read up and write a scribe note on this lecture, so you can understand these things properly. So and then you can so basically what this gives us is an understanding of the community structure of the network. Then there is another important concept called centrality. So there are some locations or some variables which are very central to the network. That is, they influence many other variables. So such things are known are said to be the central to the network. For that is, if some like whenever that variable changes, lots of other variables change as well, are influenced as well. So the centrality, so basically it's the centrality is the aim of the centrality network is to identify hubs. Hubs or important junctions in this kind of a network. Okay, so that is centrality, and then there are like various other properties which like which you can talk about. So like these are some results from some of the papers which we talked about. So this is the like the degree distribution of a graph. So here as you can see, so this is like like an equatorial band. So here you can see that the like if you consider any location here, on an average they have a large number, they have a large degree. Okay, so exactly what is the scale? I mean, how they these numbers 0.5, 0.47 they are coming. So to know that we have to understand the paper. But basically, it's like saying that if you consider any two locations here, they will have high degree. But if you consider locations beyond this tropical belt, they will have much lower degree. So in a sense, it's like this is a region which like either it's like it's a community of its own, like like where everything influences or everything else, or it can be like a very big influencing region which has like which is strongly connected to many other locations outside, even though the other locations may not themselves be connected. So that is like whatever it is, it shows that this is a region of like importance on which lot of other regions also depend. And then, as I was saying, people often try to study this this degree distribution as a function of time. That is two locations, let us say, are some distance apart. Then what is the probability that they will have an edge between them? So that can be studied as a some kind of a like with these kinds of plots. And then like this connectivity and so on, people like people try to understand these kinds of things to, and basically to identify some homogeneous regions which like which is strongly connected. So again, once again, you see that it's, if you consider the equatorial region, you will see strong connections. However, beyond the equatorial regions, that such connections, such strong connections are less and less frequent. Then we can I already talked about teleconnections. So we can like using these kinds of networks, we can try to identify teleconnections. That is basically, so identification of teleconnection basically means you are given a graph and you have to find long paths. So it's like you are saying that from one variable to another variable there is a path, from another variable to a third variable there is a path, from third variable to fourth variable there is a path, and so I mean there is an edge and so on. So basically a path is a is a sequence of edges like this. So along which influences can travel. So given given this kind of a network, you can actually study teleconnections by tracing different edges and like identifying paths like this, along which one like through there is two variables or which are located quite far apart from each other, how they can influence each other through a chain of events, each of which is or each step of which is indicated by a path. So I mean by an edge and so on. So this is one way in which this is one paper in which people have used these kind of networks to identify such teleconnections. Say from something near Japan to something near Iceland. So just imagine how far these two locations are, but like they have been able to find some kind of a path which connects this like these two locations and so on. So again, these are these kinds of studies. So like so what so like they are basically trying to so this is an like okay, so this red link, this actually shows that something here, that is one variable here, shows a strong correlation with another variable here. So now that only shows that there such a teleconnection exists, but it still does not show us why it exists or how an influence from here may travel here. So for that, what they are trying to do is path tracing. So they actually have found a like a path, which is nothing but a sequence of edges like this, by which influence of one variable here may reach or may affect another variable here. So this is the analysis which they have done, right? So and so on. So yeah, so this is the this is the way it's used for to identify teleconnections. And it's also used for like a synchronization of extreme events. So like I have already given an example of this kind of thing. So so people have done this kind of extreme event synchronization. Like for example, like here basically they are showing that so whenever one kind of extreme event happens, that is when one kind of like positive anomaly happens in this region, it's usually correlated, or it usually is coincided with a negative anomaly in this region. That is, you can see the blue, this indicates a positive anomaly, and red indicates a negative anomaly. So like of some particular climatic variable, so this ACBRA, ACR, ACSA. I don't remember what exactly how exactly these are defined, but you can understand that when like if at a given time these locations are having a positive like extreme, like I mean not just a positive anomaly but a positive extreme, the negative extreme here happens simultaneously. So these kinds of things can be understood with the help of climate networks. Okay, now geophysical, other kinds of geophysical networks may also exist, and it's need not be that I have mentioned that the different nodes usually represent a variable at a particular location, but that need not be the case. So here it's like each node represents one particular geophysical variable. Like for example, here this is the extreme temperature. Here this is the concentration of carbon dioxide, this is the concentration of methane, carbon monoxide, hydrogen, and so on. And it's like what they are trying to do is trying to understand whether one of these influences another or not. So two of these variables are considered to be connected by an edge if they influence each other. So and then, of course, as I said, these kinds of networks can also evolve over time. That is, new edges can appear, new edges can disappear, and so on. So yeah, so this is the story of climate networks, or sorry, not climate, but geophysical networks. And so again, like you are welcome to prepare scribe notes based on this topic, or like you can collect some of the research papers which I mentioned, and you can write some kind of a detailed summary of those works. You can write a scribe note on the different criteria which are used for defining climate networks, or the different properties which I were showing, the centrality and so on. Or if you want, you can use it for a seminar or project topic also. Okay, so yeah, so with that we come to the end of today's lecture, and we will meet again tomorrow at 4 p.m.